Desmond Lawler is the Nasser Al-Rashid Chair in Civil Engineering at the University of Texas at Austin, where he's also been named a distinguished teaching professor. As a master's student, I had the opportunity to experience Dr. Lawler's teaching firsthand. And even though I had little interest in the subject matter at the time, his class in physical chemical treatment processes was one of the best classes I've ever taken, both in terms of the amount of information that he conveyed to us and the way he made us all better problem solvers. In addition to that, Dr. Lawler has always been there for myself and for other students when we've needed advice and mentoring. So it's no surprise to me that he's been named the ASEESP Charles R. O'Milliot Distinguished Educator and Distinguished Lecturer. So thanks for coming.
Thank you very much. So thank you very much for having me today. It's a real delight to be here at the University of Michigan, and obviously it's a program that I've known a lot about for my entire career, and one that I have a tremendous respect for. So it's a real honor for me to be here, and I appreciate everybody coming today. I have quite a number of slides to try to get through, so I'm going to jump right in here to talking about what we're doing today. So I wanted to start by not talking so much about the subject matter itself, but just kind of a general way I like to think about research. I think one of the things that we do in research is, or the thing we do is ask ourselves a question. And I think in general in our field in environmental engineering, we can translate that question into a mathematical formulation. And when we solve that math, we basically have an answer to the question that we are asking ourselves. And alternatively, we can translate that question into an experimental investigation and do our experiments, get our results, and those results, in essence, are an answer to our question. And in some cases, we have the luxury of doing both of these things, and then we have two answers, and in this comparison of the answers, we can really find out whether we know something or not. And in rare circumstances, they actually agree, and then we probably really do understand what's going on. But oftentimes, there's some lack of agreement between those two things. And in that case, we can oftentimes discover that, well, we really didn't make this translation very well, or we didn't make that translation very well, or we didn't really know how to run those experiments very well, and we got poor results and whatever. And then we go back in, and we improve all of that. And we get to the point where we actually get an agreement between these things. So that's what I like to try to think of doing in my research, and I'll try to show you some examples of that today. So I have in this talk about desalination, I have several kind of introductory slides about what the issues are and whatever, and then I start talking about the desalination process itself and what we know there. And so I just kind of want to set the stage here over the next several slides. So only 2.5 to 3% of all the water on Earth is fresh water, and 2/3 of that fresh water is locked up in glaciers and ice caps. And so the renewable annual water supply is only a very small fraction of the water on Earth, and a lot of that we lose by evapotranspiration. So when you do all the math of this, we really end up with the possibility of having severely limited water resources for our, freshwater use. This is an interesting slide. It goes back more than 100 years. It's 1900 here, and 2005. It shows the gross domestic product of the United States on the one ordinate and the U.S. water withdrawals on the other. And you can see that these two things were tracking quite closely, as long as you're creative in how you generate the axes here, until about 1975. And since then, the total water withdrawals in the U.S. have been essentially flat. And of course, the gross domestic product has continued to rise dramatically. And if you break this down into different sectors, what you find is that, like, the municipal sector for supplying drinking water has actually continued to rise, and the agricultural sector has reduced somewhat, to lead to this relatively flat situation here. But despite that flat situation, we have tremendous water stress in various parts of North America here. And I live in the southwest U.S., and the red is bad in terms of water stress. Up here in Michigan, you're maybe mildly stressed at times, but generally fine. And of course, Florida has substantial water stress in here too, which basically means that these red areas are places where there's just really not enough fresh water to do what we think we want to do, and we are reducing our water supplies rather dramatically. And this is what leads to the interest, I think, in desalination as a way to go. So when we think about desalination, there's really a distinction between seawater, taking water out of the oceans, and brackish water, which I've kind of defined here as being 1 to 10 grams per liter. There's really no reason to put this upper limit on here. It's basically anything less than seawater, but the waters that we're using for brackish water desalination typically fall into this range or maybe slightly higher than that. And so they have this, values of total dissolved solids in here. And in seawater, basically, you're talking about coastal plants for desalination plants. The recovery, the fraction of the water that we put into that plant that we actually get to use as drinking water or fresh water is in the range of 30 to 50%, and the rest is then the concentrate, and that concentrate we can typically dispose of in the sea, which is relatively easy. The other thing that we have, brackish water, is the other supply, and in this case we were talking about inland situations where you're using groundwaters, or in some cases surface waters, but typically groundwaters. And the recovery is much higher, 65 to 90%, with 80% being a typical value. And, but that leaves quite a bit of still concentrate that has to be disposed of. Just for comparison, a freshwater plant, a typical drinking water treatment plant, recovers essentially 99% of the water, with only 1% going out of the water going out in the sludge from those plants. So the difference here is dramatic in terms of the disposal of the concentrate that we have to get rid of. And to me, the concentrate disposal is a central question to what we do in desalination. Again, just so I've already used some of these terms, but just so we typically think about membrane processes. We use this kind of generic diagram to describe the membrane here by this diagonal line. The feed water comes in. What passes through the membrane is clean water, which in our case, our typical interest is in drinking water. And the waste, we call the concentrate, is what doesn't make it through the membrane. And again, the recovery is on a percent basis is how much drinking water we get versus how much feed water we get. And those are the numbers that I just was quoting. 80% typically for inland desalination and 30 to 40% for seawater desalination. I'm not going to go through this in detail, but I think probably you're aware of reverse osmosis membranes. The overall plant looks something like this in these pressure vessels. Inside each of these pressure vessels, there's a few of these modules, and inside those modules you have the membranes themselves, which are so-called spiral wound membranes, as indicated by this picture here. Water comes in the end and goes through the membrane and then makes its way through the spiral out into this central collection pipe and out. And the concentrate goes through the membrane goes through this whole group on the other end and comes out the other end. So that's what these things look like, and so these plants, we do operate these plants. We do have them, and I think if you're talking to people outside our field and they say, well, what's going on with desalination? It's not unreasonable for you to say, oh, desalination is simple. We know how to do this. We take salty water and we put it through a membrane process and we end up with clean water, and we know what we're doing. And it's not an unreasonable answer to say that. But I probably wouldn't be talking about this if it was really completely true. And so I want to say, really, desalination is not quite so simple, and I want to highlight a few of the ways in which it's not so simple and what we work on. So the first is the desalination process itself. There are details of that are certainly not that simple. The second is the post-treatment, and I don't think people think about this very often, but the fact of the matter is that reverse osmosis membranes work so well that the water ends up being too clean for a lot of purposes that we want to put it to, And so we have to think about post-treatment. The third thing is pretreatment, that we have this water that we're taking out of the ground or out of a salty surface supply. And if we put it just straight into the membrane process, we're going to not operate very well. And so we often have to do some substantial pretreatment to get the desalination process to work well. And finally, the concentrate management. What do we do with this concentrate? How do we deal with it, and whatever? So I want to talk about each of these things. I'm only going to say a few words about the desalination process itself. I'm going to say even less about the post-treatment, but I will comment on each of those things. And then most of my talk is devoted to some ideas about pretreatment and some examples that we've done in our research, and then even more so talk about the concentrate. So this is where I'm going over the next 30, 35 minutes or something like that. So on the first part, the desalination process itself, what are some of the challenges, what are some of the opportunities that we need to think about with respect to this? So thermodynamics is actually the heart of this game, and it's the heart of the energy-water nexus, which is, of course, something that we're thinking about in a lot of ways in our field right now. But in terms of desalination, the thermodynamic limit is the bottom line of this thing. And the question is really, how close can we come to getting to that little energy use that is the thermodynamic limit and still produce desalted water? And so part of the deal is to create new membranes. And there's been a tremendous effort over a number of years to improve the membranes themselves, both to reduce the fouling and increase the specific flux. The specific flux being the amount of water per unit area, per unit time that you put through, divided by the amount of pressure that you apply to do that. That's what the specific part of this is about. And then there's been developed these pressure recovery systems, which are really quite amazing, so that you have to apply a lot of pressure to these reverse osmosis membranes. And it turns out that the mechanical engineers have developed ways to, in essence, recover a lot of that pressure to, in essence, reuse it for more than one pass of water through the system. And these two developments have really dramatically improved our ability to come close to the thermodynamic minimum. And that minimum is shown in this graph here. I wish it started at 0, but it doesn't, and it goes up to 3.5. I want you to pay attention to these units here because we're going to return to them later. Kilowatt hours per cubic meter of water produced. And you can see it goes up to around 3.5 in these units. And the percent recovery, what fraction of the water we actually get to use as drinking water, is on the abscissa here. And of course, if you try to recover more and more water, you're going to have to spend higher and higher energy amounts to do that. And because the solubility of things is a function of temperature, at higher temperatures, it takes a greater amount of energy to separate the salt from the water in here. So this is, kind of our goal is to use energy that approaches these lines depending on what recovery we have and what temperature that we're at. And this is a graph that shows how the actual energy use in seawater desalination has come down over the 40 years or so since people started doing this. And again, we have the same units here in kilowatt hours per cubic meter. And you can see, and this line here represents the thermodynamic minimum for the first pass RO, the first RO in a series, getting 45% recovery, which is pretty low on that curve, but this is kind of where we operate most of these systems at. And you can see there's been a dramatic decrease in the energy used to do desalination, which is why it is now pretty feasible to think about doing this, whereas in earlier times, people would just say, well, the energy use is so crazy that we can't think about it. And so you can see now that we're down to maybe a little bit less than twice the thermodynamic limit. This is the last data I could find, but I think there's been a few improvements since then as well. So we're doing pretty well on this in this improvement. And again, that's mostly thanks to our chemical engineering friends and our mechanical engineering friends who have made these advances that make that possible. Post-desalination, again, I mentioned that basically nothing makes it through an RO membrane. I mean, that's not quite true. You can measure some contaminants that make it through at small values, some sodium, some chloride, but not very much. And so basically the water becomes so clean that it's corrosive and it would taste terrible. I don't know if you've ever tasted distilled water in the lab. It doesn't taste like much. You really wouldn't want to drink it all the time. So we add things to the water to make it useful for us. And if it's drinking water, we want to put in some calcium and magnesium so that it tastes well. We add some carbonate to adjust the alkalinity. In some cases, it's conceivable we might be able to get these things back in the water by blending some untreated water with it, but it would take a very unusual circumstance for that to be happening. Sometimes you might have to strip some soluble gases out of the water. You have to add some sort of polyphosphates or other things for corrosion control if you're going to use this, because these are highly corrosive waters that come out. And of course, if we're going to put these into a drinking water system to spread into a town, we probably want to have some disinfection, residual disinfectant in that water. And so we have to do all these kinds of things. I just want to note in passing that this is, if you buy bottled water from, like, Dasani is the Coke brand, and I can't remember what the name of the Pepsi brand is. What they do is they take municipal drinking water, they do desalination and put it through RO, and they take everything out, and then they add some things back in, and their different formulas for what they add back in are a little different, and that's why they taste a little different. So if you want to waste your money on that, that's what they do in there. But again, I mostly want to talk about some of the pretreatment issues and the concentrate management things, and I'll spend a little bit more time talking about these things. So we have to do biofouling control, disinfection prior to the membrane, because we don't want biofilms growing up on the membrane processes. So almost always there's some sort of disinfection process prior to the membrane. It might be chlorine, it might be ozone, it might be ultraviolet light. We do particle removal processes, and we have to do scaling control, because the thing that limits the recovery is precipitating onto the membrane surface, and that's called scale. And we want to prevent that from happening, and so we have to have some kind of scaling control. And I have a little detail about a few of these things on here, so let me go back through these. So if you use chlorine, most of the membranes that we use don't withstand chlorine, and so if you do chlorination, you have to do dechlorination afterwards in order to save your membranes, or else we have to develop chlorine-resistant membranes, and there's been a lot of work on that in recent years. If you use ozone, that's all well and good. It's a great disinfectant, but if you have any bromide in your water, you're going to form bromate, which a decent amount of that will actually make it through an RO membrane. And so you're going to end up with bromate in your water, and that's not a good thing for our drinking water. So you have to be careful about how you do your biofouling control. Particle removal is really conventional drinking water treatment. All the processes that we use in a surface water treatment plant are oftentimes used in these kinds of plants, depending on what the source of the water is. If it's seawater, there's a lot of pretreatment. If it's a groundwater where there's not very many particles or whatever, this might be pretty minor. Interestingly, sometimes the pretreatment is another membrane process, an ultrafilter in there. But again, depending on the water source, this may be a serious part of what goes on. So like the Tampa Bay plant in Florida, which they use water from the Atlantic Ocean, they had enormous problems getting that thing started, and it all had to do with improper or insufficient pretreatment processes in their water. And scaling turns out to be a big issue in RO systems, and controlling that is important. And so typically we'll add acid to prevent a lot of things that will precipitate at higher pHs, and so we control that by pH control. We use some organic anti-scalants. I'm going to talk to you about some of the phosphonates that are used. And then for silica control, we oftentimes have to do a precipitation prior to the membrane to do that. And many of the waters that we think about doing desalination on have substantial silica concentrations in them. And that's, in fact, what I want to talk about as an example out of our research that we have done. So the Rio Grande, I'm sure you all know, is the border between Texas and Mexico. And it turns out that it's relatively high in silica, as are many of the waters in South Texas and northern Mexico, groundwaters and surface waters. So there's about 60 milligrams. We typically report silica in terms of SiO2, but that's 28 milligrams as silica itself. Calcium is relatively high. Magnesium is not so high. Alkalinity is reasonable. And the pH is around 8 of Rio Grande water through a large stretch of the Rio Grande River. If you do geochemical modeling, precipitation modeling, solubility, equilibrium modeling, and think about what's going to happen to silica, calcium, and magnesium as you add lime, just straight softening, if you will, it turns out they'll all precipitate. And so calcium, of course, when we do softening, that's what we do. I understand we do that in the Ann Arbor water treatment plant. This is what they do. If you don't add any extra carbonate, you'll run out of carbonate, and then you'll start adding calcium back into the water. The magnesium also goes down mostly as a function of pH. You precipitate magnesium hydroxide. And silica will also be reduced in here. So one way to think about pretreating for a desalination of a water with high silica is to use softening. And we did this in our lab some years ago. And these are some results of a few of the batch experiments where we're adding lime. We're adding soda ash, depending on which is the sodium carbonate, because we added so much lime we would run out of the natural carbonate. And we also were adding excess magnesium into the water, and this graph shows what happens as a function of magnesium added for 3 different treatment processes with respect to the lime. And again, these are the initial values on here. And you can see in terms of silica, which is the primary thing we were going after, is that we could reduce the silica concentration by all of these treatment methods pretty well, and that magnesium was a big part of accomplishing that in here. And so this looked like promising technology. And so we look at some results from slightly different experiments here where, again, we have 3 additions of lime, magnesium, and the soda ash in here. They're not terribly different, as you can see, but we're adding more magnesium here than here, and we're adding more lime than in the other 2 in this. And we measured after the results of this silica, magnesium, calcium, what the alkalinity was afterwards and what the pH of that was. So here's the raw water. Of course, you're adding that much lime, you're raising the pH. All of these are about the same. And you can see that we have different amounts of all of these things, with treatment 3 leading to the greatest amount of silica reduction. So we took these and did all 3 of these in a laboratory scale reverse osmosis system. This is in Benny Freeman's lab in our chemical engineering department. And there's actually 3 tiny little membrane pieces in here, and these were operated in succession. Then we could measure what was going on in all of those. And we did this for lots of different treatment systems, including these 4 waters here. Rio Grande water without any treatment at all, and then the 3 treatments that I indicated to you a moment ago. And we measured what the flux was, specific flux, again, the volume of water per unit time per square meter of membrane surface per unit of pressure. And what happens in here is low is bad, okay? So you end up with low flux without treatment. And as you did these various treatments, you could increase the amount of flux that you got. And it turns out that pretreatment 1, which did not have the lowest silica concentration, turned out to give us the best result in terms of the least flux decline through this process. And it's maybe a little bit unfair how we interpreted this in terms of recovery of the water we would get, but in any case, that also leads to having the greatest recovery of the water. So the point is that the silica removal, and for that matter, removing some calcium as well, resulted in far better flux, and therefore the ability to recover much more water through that process. So that's, again, one example, and I guess the overall point would be that you need to kind of be site-specific about what pretreatment is necessary in your system in order to create a system that works the best for you. And this kind of treatment is relatively cheap in comparison to the RO process itself, and so therefore increasing the flux like this is definitely economically worthwhile. And then I want to change the focus now to talk about concentrate management, and this is a subject that I think is really important when we think about inland desalination. And again, I indicate what recovery means in here. So to me, in inland desalination, this is the biggest challenge that we face, and it's because the recovery is limited, and intrinsically, recovery and concentrate are directly related to each other. If we increase the recovery, it means we would decrease the concentrate volume that we have to dispose of. And so we thought we should consider various treatments of the concentrate in order to then be able to recover more water in a further process. So we actually did two different ways, and I'm going to show you results from both of these. So what happens in these systems is that you have reverse osmosis systems in series, and the concentrate of one becomes the input to the other. I'm showing 3 in series here. Usually it's just 2. And then we imagine putting an electro dialysis system after this, which is another membrane process, and that would increase our product water and decrease the amount of concentrate that we had. So that was one of our systems, and the other one looks more complicated, but it's actually probably simpler. So in this case, what we do is we take the concentrate from an RO unit. We do an antiscalant oxidation because we've added antiscalants into here to prevent precipitation from going on. But now I want precipitation to happen. So I want to destroy that antiscalant with an oxidation process, then allow precipitation to occur, do a solid liquid separation where we take that precipitate out. We end up with sludge that we have to dispose of, but we also end up with cleaner water, which we can then put onto another RO unit and increase our product water. So I'm going to talk about both of these processes that we've used in our lab. Lots of results on here, and this has to do with antiscalant oxidation, where we're using a combination of hydrogen peroxide and ozone, same amount of ozone and increasing amounts of hydrogen peroxide in here. And we're measuring the results very simply. This is a phosphonate antiscalant. And so what oxidation would do would be to release the phosphate. So if we just measure the orthophosphate, we know how much we've destroyed of the antiscalant. And this had an initial phosphate concentration of around 1.3 milligrams per liter in here. And so basically anything higher than that came from oxidizing the antiscalant. Now, what are all these results about? Okay. So the first results I'm going to talk about are down here in the bottom. If we have just borate in the water, which we were using as our buffer to make sure that it wasn't interfering with anything, basically nothing happened. That's good. We have sodium chloride in there as well. Also basically very little or nothing happens. And so that's interesting, but basically this isn't doing very much at all. I mean, we're producing a little bit, but not very much. It turns out if we add some bicarbonate into the system, we definitely get a change, and we're definitely increasing with a function of peroxide in there what's going on, and that has to do with how bicarbonate and ozone and peroxide all mix, and we'll talk about that in a minute. But if we add calcium to the water, wow, we get way, way, way better results in here in destroying the antiscalant. And if we add now more complex, we add the sodium chloride and the bicarbonate and the calcium, it also does very well. And we add a little sulfate, and it also does well, but a little bit worse. We add magnesium, again, quite good, but a little bit worse. And we add both the magnesium and the sulfate to the water, which has the calcium and the sodium chloride in it. Again, about the same in here. We add some iron, things definitely get worse. We add some barium and nitrate, things are also about the same as nitrate. Wow, what's going on in here? There's lots of results. So this is pretty complex chemistry, and I don't have time to go through all of the details of all of this, but it's all the ones that did really well contained calcium. These two contained calcium, but also contained iron, ferric iron, so they made things a little bit worse. And all the ones down at the bottom had no calcium in it at all. So calcium is clearly a player in what's going on in here. Let's see if we can try to explain what the anti-scalene oxidation pathway might be under these various circumstances. So it turns out that when you add peroxide to the water, so as you move to the right on this scale, you should be producing more hydroxyl radicals because that's what hydrogen peroxide does in here. And if you get basically horizontal line on here, then the hydroxyl radicals are not a big player in what's going on, and so it must be the ozone itself which is doing the oxidation in here. When you added the iron in here, then you don't get a horizontal line. You definitely get a sloped line in here, which says that in that case, the hydrogen peroxide, or in other words, the hydroxyl radicals, are an important player in the oxidation of the phosphonate that occurs in here. And if you add terbutanol to a system like this, what happens is that terbutanol is a hydroxyl radical scavenger. So even though you're going to produce these things, that terbutanol is going to destroy them just about as fast as they're produced. And so what happens when you had the system with calcium, with and without terbutanol, you basically get more or less the same results, which is further indication that the hydroxyl radicals are not important when calcium's in the system. But when you had this other system in here without calcium, then you got certain results without the terbutanol and a dramatic result, a change or reduction with. And so that's a further indication that the hydroxyl radicals are an important part of the oxidation when you don't have calcium in the system. So with calcium, you're getting a reaction with ozone, and without calcium, you're getting a reaction with hydroxyl radicals, and all of these results indicate that that's true. We also did some interesting experiments to look at what the function of pH was in here with no peroxide and with peroxide in here. And in essence, there's a difference, but they're very closely related, and their pH effect is essentially identical in here. And when you added terbutanol to a system that had the hydroxyl radicals added, or the peroxide added, which form radicals, you also get essentially the same results in here, which again is really part of the same story of the hydroxyl radicals don't seem to be very important in here. But wow, what a function of pH. Okay, this is really substantial. And when I first looked at this, I thought, well, the peak of this is near the pKa of the carbonate system. That must be important in here. But it turns out that that was not true. So again, doing some chemical equilibrium modeling, we discovered that the complexation of the phosphonates with calcium was known. And all these, as a function of pH, you end up with all this different speciation of the various complexes with calcium and the phosphonate. And if you pay particular attention to this one, you can see that it peaks at right around pH 6, where we had gotten the best result. So it turns out that the explanation is that when you have calcium in this phosphonate, you end up kind of changing the conformation of the phosphonate to the point that ozone can attack it. And that's what allows that phosphate to be released in here. So very interesting kind of oxidation pH, complexation chemistry to figure out what's going on with respect to this, and then dictates how you would have to do this process in reality. Again, if you don't have calcium in the system, you basically get very little happening. Again, further confirmation of what's going on. I'm going to more or less skip the next couple slides here. Basically, we did this with several different kinds of anti-scalants, and if we ozonated, basically they all gave us results that were very close to the equilibrium values that we could get in precipitating calcium in the solid liquid separation process following the oxidation. And we could increase the recovery that we could get rather substantially by doing that according to the modeling that we did. So basically, this process would work is the point of that. Okay, so now a little bit about electrodialysis, the other process that we used in here. I'm kind of imagining that most of you don't know very much about electrodialysis. It's not a very common process. So it is an electrical system, so we have a cathode and an anode. In between, we put cation exchange membranes and anion exchange membranes in alternating pairs, and real systems may have 100 pairs of these things in here. There's like 6 pairs shown in here now. We put water in the bottom and let it flow up through these things. And what happens is that a cation will try to make it toward the cathode by the electrical energy that we're supplying, but it can't make it through an anion exchange membrane, so it gets blocked. And an anion tries to go to the anode, but it can't make it through a cation exchange membrane, so it's blocked, and these ions are just going to flow right up without anything good happening to them. But in the opposite channels, then the anions try to make it to the anode, and they can make it through the anion exchange membrane, so they leave this channel and get into the next channel. And similarly, the cations can make it through the cation exchange membrane and make it through into this channel. And so this channel here becomes clean with respect to ions, and the adjacent channel becomes dirtier. It has all the ones that came in plus the ones that have come in from the adjacent membranes. And so if you collect all the clean water, which we call the diluate, in one set of pipes, and you collect all the dirty water, which we call the concentrate, in the other set of pipes, you've now made a separation of the ions, and you end up with clean water coming out the diluate here. And so, and when this is basically the current that goes from the anode to the cathode that's being carried by the ions that are moving. That's how this works. You also create gases, oxygen at the anode, hydrogen at the cathode, as you do in most electrochemical systems. And so that turns out to be a little bit of a problem in these systems. So we did a series of experiments with this. We have an electrodialysis system, a laboratory scale electrodialysis system. We had a diluate reservoir, and we pump through here and back, so it's a recirculating system. We have a power supply on here as well. Similarly, we have a concentrate reservoir that we pump through a different place and take it out and recirculate it around. And because of that those gases that are formed at the electrodes, you also need an electrode rinse so that you separate that water from the rest of the water. And so we had a third reservoir for the electrode rinse that would also go through here and just go through by the electrodes in there. You measure the flow rates. You measure the pressures at various places. You measure the pH, the conductivity, and the temperature at various places, and you end up with quite a complex system that looks like this. So this little puppy right here is the electrodialysis system, and this is the power supply, and here's the pH, conductivity, and temperature measures, and here are the reservoirs. Here's a couple of them here. Here's the third, which we're measuring the weight of transfer in here, because you do move a little bit of water and not just the ions in here. And here's the system that both measures what's going on and controls what's going on in here. And if you have a really great PhD student like Shane Walker, he can build all that, and you walk into the lab and it's done, and you haven't had to do any work to do it, except you've had to buy all the equipment to do this. And so this is what it looks like, okay, with the results. So we're measuring conductivity in here, and of course we're trying to make clean water, and so the diluate is getting better as a function of time, and the concentrate is getting worse. The conductivity is going higher. So we're separating the ions from the liquid into these two separate things, and of course we started with an identical kind of water in both the concentrate reservoir and the diluate. And as you increase the amount of voltage applied per cell pair, from 0.5 to 1.5 volts per cell pair, you can see the process happens much faster if you supply more voltage to the system. And if we look at those same results in terms of removal ratio, in other words, just really focusing on the diluate, you can see that you can get virtually 100% removal of ions from the diluate in reasonable amounts of time with what happens in real systems, reasonable amounts of voltage applied as well. The specific energy consumption, remember I told you to focus on those units of kilowatt hours per cubic meter. Here they are again. And you can see that the kind of energy we're talking about is in the ballpark of what I was talking about with the thermodynamic limit for separation in there. As a function of removal ratio, and again, the higher the voltage you apply per cell pair, the more energy you use to make that separation happen. So if you look at, say, trying to remove 80%, you can get there with 1.5 volts per cell pair. You can get there with 0.5 volt per cell pair, and you use a lot more energy to do that. But of course, it happens a lot faster, and that's the trade-off that you have to make in the engineered system. OK, so we kind of pushed the limits on this a little bit to take our original system, which was 4 times basically the groundwater. So what you would get out of the RO system before you started scaling would be the input to this kind of system. And we said, OK, if you did that separation once and then you took the result of that and put it into another system and then did that a 3rd time, you would end up with getting diluate that, eventually, if you ran this long enough, could get to be very, very clean. And the point is that at this point, we're way, way higher than the saturation limit with respect to precipitation. But in this system, because of how electrodialysis works, you don't really embed this stuff on the membrane. And even if you start to precipitate, it's going to go out in your concentrate, and you end up with a system that you end up being able to use the diluate on very, very well. So this is electrodialysis. I think this is maybe the niche that electrodialysis should be used for. Just a few brief words about modeling this stuff, and I don't have time to go into this in great detail, but we looked at what the flow pattern would look like through here, and of course next to the membrane you have basically no flow, and in the middle you have kind of turbulent flow in here. So we imagined that this was basically had a velocity profile that looked like this, and then you also end up with concentration profiles that also have looked like that. So it turns out that if you use the Nernst-Planck equation in the central part, you don't have any diffusion going on because you have a flat surface there, but next to the membranes you have diffusion that's important, and you can model all this stuff. So we basically tried to model our system looking at steady state plug flow through the membrane process itself with a steady state solution of what's going on the electrodialysis system along the flow path next to the membranes. We used an empirical function for the conductivity related to how much the ions that we had in the water would be. And then in terms of the overall system, we're looking at this as a dynamic batch recycle. So the batch is changing all the time as you go in those reservoirs. So this is basically what's going on in the reservoirs in here. And when you do that, basically this is what our model predicted. And the lines represent the model results, and the data are the circles and triangles. And you can see we essentially fit it perfectly, or nearly perfectly in here. But just so we didn't think we were too great, we looked at it other ways. The current density, which is also something you can measure, also was modeled very, very well in this system. But when we looked at what was going on with individual ions, and we did some experiments where we measured what's going on with individual ions, our model results basically said the results are so this is conductivity removal, and now the specific concentration of calcium and sodium on the top and chloride and sulfate on the bottom. And you can see our models were insensitive to the change in voltage applied, but the results were not insensitive to that. And also in say predicted we always underpredicted what would be in the concentrate and overpredicted what would be in the diluate, and vice versa for sodium. So it's not perfect, and there's still work to be done on here, but this is a pretty good modeling effort in here. Okay, so let me try to wrap this up. Taking a lot of your time this afternoon, and try to pull this together. So I think that desalination itself can now be considered a relatively straightforward process. We know how to do it. There's not some issues, but I think we're in pretty good shape there. We can still improve the membranes. Some of that improvement may enable us to reduce the pretreatment requirements, which would be nice. And we can increase the specific flux with more extensive pressure recovery or with some further improvements in the membranes. I think there is work to be done there. And again, most of that kind of work is not being done by environmental engineers primarily, but it's being done by mechanical engineers and chemical engineers. The post-treatment of desalinated water is generally straightforward. We know what we need to do. We know what kind of water we want, and we know we just add things to it, and we end up with a water that we can use for the purposes that we want, and that typically means that we want something that's non-corrosive. Pretreatment, I think, imposes a lot of technical difficulties for us depending on the water. It's very site-specific. Certain chemicals are frequently present in the kinds of waters that we want to desalinate. Silica, boron, bromide, and they all impose various kinds of pretreatment issues and treatment issues that are important. And we have to make sure that we use biofouling control that is compatible with the membranes in there, and we have to think about that pretty carefully. And lastly, I think that the concentrate management, again, is the biggest challenge that we have. And the treatment of the concentrate to improve the overall recovery, I think, is the most promising option. I showed you electro dialysis. I showed you precipitation with further reverse osmosis treatment. But I still think that there's more research that needs to be done there. And again, it oftentimes becomes kind of site-specific. In my opinion, many of the current solutions are not solutions at all. And deep well injection, land disposal, sewer disposal, people do these things, and I just think as when the environmental agencies wake up and realize what people are doing, they're going to say this doesn't make any sense. Okay, and in particular, something like sewer disposal, which is allowed in many places, is completely nuts. I mean, we put things in the wastewater treatment plant that the wastewater treatment plant doesn't do anything with, and we're just adding salt into the environment, which is not something we want to do. So, but it happens, and I think it needs to stop. And zero liquid discharge and resource recovery of these minerals that we have in here is really, what our goal should be. And it's probably not technically feasible at this point, but it should be, what we have our sights set on in this arena. So with that, I would say desalination is really not so simple, but it is quite feasible. And again, I try to highlight some of the things that I think are important here. And with that, I want to acknowledge, I've shown you the work of several PhD students here. Lauren Greenlee, who's now at NIST in Boulder, Colorado. Yoongi Kim, who's an assistant professor at McMaster University. Rocio Pacheco works for Jacobs Engineering in Dallas. Shane Walker is an assistant professor at University of Texas at El Paso. My colleagues, Benny Freeman and Lynn Katz, without whom I can't seem to do very much of anything. Water supply. The financial support from grants from these people and various kind of fellowships and kind of a contract for these people is where I got the money. And so with that, I will say thank you very much and be happy to take questions.